Bueno, hago la presentación en español y luego ya pasamos al inglés. Nada, pues como sabéis, este es otro seminario más dentro del ciclo de seminarios de dirección, que son seminarios transversales que creemos que son de interés para todo el instituto y para muchos de los miembros de aquí. Y en concreto hoy para nosotros es muy importante, porque es una decisión estratégica del centro, el conocer qué posibilidades hay en IMDEA Nano de fabricación. Como sabéis, la fabricación en nuestro centro es una asignatura pendiente. Tenemos una carencia en cuanto a facilidades para poder fabricar dispositivos, para llevar a estos materiales que creemos y que crecemos hacia algo mucho más aplicado. Y la estrategia que vamos a desarrollar es hacer algo aquí que nos permita, bueno, pues aprender a funcionar, lo que hemos llamado una especie de sala gris, que nos permita jugar con estos materiales para luego hacer cosas más serias o dispositivos más serios en otras salas de fabricación que estén en el campus y que sean accesibles. En concreto, también ha pasado otra cosa nueva este año, que es que somos unidad asociada con IMDEA Nano, por varios motivos. En muchos de los investigadores de este centro, que ya estamos colaborando con ellos, parecía una cosa obvia que fueran una unidad asociada. Eso implica también que tenemos una facilidad institucional para acercarnos allí, para trabajar allí, para compartir esos recursos. Idealmente nos gustaría que esta unidad asociada llegara más, incluso a poder pedir instrumentación que esté bien allí o bien aquí, que pueda ser de uso común. Y bueno, por eso le hemos pedido a Daniel que venga hoy a contarnos un poco qué posibilidades tenemos, qué se hace allí y bueno, para conocer un poco estas posibilidades dentro del campus, además, ¿no?
Muchas gracias, José Ángel.
Pues venga.
Un placer siempre venir aquí a este instituto y a esta sala y ver además muchas viejas caras conocidas, amigos. Y nada, I'm going to switch to English now. José Ángel mentioned this is the nanofabrication facilities, but this is not of IMDEA Nano, but of the campus of the Excelencia UAM+CSIC, right? Because this is how this facility was born. This was a joint venture between several institutions. You have the logos there, Campus de Excelencia, IMDEA Nano, and the Centro de Astrobiología, which is also un centro mixto del CSIC-INTA. When José Ángel called me, I thought, okay, this is very appropriate because I was here 7 years ago. Actually, Agustina Senjo was inviting me over to promote the use of the facility, which I'm very thankful. Thank you very much for inviting me over. And actually, it's very adequate because I think it's been like 10 years in September 2024 that we've been fully operational. You'll hear about it in a minute. Some words about me. I did my PhD at the Autónoma. I'm a physicist. Spent some time in Berkeley Lab. Then I did my PhD at the Instituto de Microelectrónica de Madrid. Now it's called Micro-Nanotecnología, under the supervision of Jorge García, which is sitting down there. Then I spent some time in Heriot-Watt. Then I moved to Toshiba. When I was in Toshiba, I was also visiting researcher at the Cavendish. And then I moved to IMDEA Nano. And right now I'm also part of many different institutions, some way or the other. I'm the director of the Madrid Semiconductor Cluster, and also participate in the Comité Ejecutivo de la Fundación Círculo de Tecnologías para la Seguridad y la Defensa. And why me and why this facility? Well, the reason why this facility is because in 2009 there was someone else in the Vicerrectorado de Investigación de la Autónoma writing a proposal together with the CSIC to become what it was called at the time un campus de excelencia, okay? And in the proposal, they were stating that they were willing to have a nanofabrication facility for the whole campus. And at the same time, IMDEA Nanoscience was being created, and IMDEA Nanoscience had in this roadmap to have a clean room. So they decided to join together, okay? And actually, in the project of the Campus de Excelencia UAM+CSIC, you can find that this will be a joint venture between the Campus de Excelencia UAM+CSIC and IMDEA Nano, okay? So this is the reason why we have created a Center for Nanofabrication in the campus, and why the Centre of Nanofabrication happened to be at IMDEA Nano. Why me? Because I was in Toshiba for 3 years, and by the time, for 3 years, my wife was here while I was living there. So at some point I wanted to move over back to Madrid. And I applied for a position at IMDEA Nano. It was a position related to nano-magnetism, which I don't know anything about, okay? But I passed to the interview, and while I was having the interview, the director of the institute told me that we were going to have a nanofabrication facility. And I've been involved in nanofabrication my whole life. First of all, at the Centre of Microelectronica first, then at Watt, then at Toshiba, I was in charge of doing a lot of nanofabrication, also in Berkeley. So I proposed myself as a coordinator of this initiative, right? Which was a big mistake. But the director asked me, why should I choose you for this project? And I replied, because I love to build things. And I think I'm really good at it. So I happened to be hired not for the nano-magnetism position, but to lead the coordination and the creation of this facility. So I arrived in 2009. Rodolfo Miranda, the director at the time of the institute, handed me the blueprints of the institute, because IMDEA Nano didn't exist by the time, and said, there, you see there you have to make it happen. So off you go. So I mean, I've been leading the architecture of the clean room, the acquisition of the tools, the hiring of the people, making sure that this is a service that everyone can access in the campus. And then I've been leading with all the tools that have been broken over the years, with the floodings, with the lack of support, with money, hunting for the money, convincing the politicians, and so forth and so on. But well, this is the scheme I came up to put the facility. Is 300, it's 250 square meters, 30 meters long, 8 meters wide, 8 meters tall, and it's divided into sections. The sections that you see in blue, these are class 100, okay? You understand what a class 100 clean room means? Everyone? Good? Then the yellow part is class 100. We have then 2 chemistry rooms. And this was 2009, and this was the clean room in 2010. Right? Actually, the clean room was the first thing ever created at the IMDEA Nano building, because it's like a matryoshka doll. It's like a small building inside the large building, but it's fully independent in every meaning. So we have our own power supplies, our own earthing, our own foundations. You see the foundations of the clean room are 20 meters apart from the foundations of the building, because we didn't want any low frequency vibrations to get transmitted into the nanofabrication tools. Okay, and then it's the floor of the clean room is a continuous flooring. It's 30 meters long, 8 meters wide, 1 meter thick, and it's being supported by a 1 meter thick foam, anti-vibration foam, and then on top of these pillars are going 30 meters into the earth. 2010, by 2012, the building was being finished, but the clean room was looking like this, so not very clean. This was a problem because many of the tools that were acquired thanks to the Campus de Excelencia were already there, so we have them in boxes for many years. 2013, the clean room was already there, it was already clean, and then we start putting all the tools inside. So we spent the whole 2014 putting tools inside. Took an awful lot of time. And by September 2014, we start offering service to the campus and to the companies. But well, this is more or less how it's looking now. You see, this is room 1 is for encapsulation. Room 2 is for thin film deposition and etching, and also some metrology. Then this is a chemistry, wet chemistry lab, mostly for cleaning or for wet etching. Then there is room 4, which is only for resist, either deposition or developing. And then we have room 5, which is for lithography tools. We have temperature control plus 21 degrees plus minus 0.5 degrees in all the rooms. Humidity control is 50% plus minus 5%. And in some rooms, we have between 40 and 100 air renovations per hour. So this means that you take a breath, you hold the breath for 2 seconds, and by the time you expel your breath, the whole air in the clean room has been fully renovated. This is expensive, it's super expensive to do, but you really need it if you want to have these tools and their specs. Well, at the time, I did my PhD at the Centre de Microelectronica. I have many friends at ISOM. Those were like the most popular nanofabrication facilities in Madrid. And I didn't want to fight over, so I tried to select tools that were non-existing in the Comunidad de Madrid at the time. And also I didn't want to fight for the space. So I tried to find application vectors that nobody was targeting at the time. So this is what we decided to aim for: space community, but also security and defense. Right, in 2014, we signed a collaboration framework agreement with INTA and with the CAB to work together. And also in 2019, after many years, and thanks to the help of the National Security Office, we have managed to obtain a security clearance for the whole clean room and for the personnel working there. So now we can work in NATO, EU, and especially in ISA secret projects. I have to say that mostly 2015 we spent our time just making friends with the tools and being sure that we really exploit all the full capabilities of every single tool that we have there. And I think that probably by 2016 we were up and running, and we were able to produce state-of-the-art devices. For example, this is a whole bar made of graphene. So over the years we've been criticized that IMDEA is making a lot of money, and we are becoming rich thanks to all the uses of the Campus of Excellence. Well, I just want to make sure that you understand that this is not the case. Over the years, total investment has been around 12 million euros, of which 2.5 million comes from the Autónoma, from the Campus of Excellence, and about 1 million comes from the CAB-INTA. And the rest is just being fully sponsored by ourselves, okay? So this is more or less how the effort is being distributed right now. So 70% of total cost and the running cost is fully paid by IMDEA Nano. And right now, the running cost is fully paid by IMDEA Nano, except with some help from the Centro de Biología, because many of the deals that we were promised, it's been hard times for everyone. So right now, for example, we were planning to share the electricity bill together with Autónoma, but unfortunately this hasn't been possible. So right now we are fully supporting revenue. Okay, how much money are we making? So running cost is around 700 grand per year. Revenue is around 150. So I mean, we are producing a big hole every year. It's not because of lack of users. I will say that we are about between 50% and 60% usage. So not close to the maximum. But I will say that if every tool will be used 100% of its useful time, total revenue will be around 300 grand. So we will still, because it's not our commitment to make money with this facility, but to make sure that the Comunidad de Madrid scientists and the Comunidad de Madrid companies have access to a state-of-the-art nanofabrication facility. Okay, and we will keep like this forever, as much as we can afford it. Okay. There has been other costs. This was me before the project, normal guy. This is me in a standard day. So if someone else offers you to do a project like this, say no. Learn the lesson. Okay? No, I'm joking. It's been a privilege. It's been really good fun, right? But I mean, it's been super hard. I have to be honest. Key factor. So we can talk about the money, and if you have the money, you can buy many tools. But this is not going to take you to lead and to compete with the outside world, with other scientists in other regions or other scientists in other countries. What really makes the difference is the people. So I'm privileged to be working with all these guys that, I mean, they are super professional, and they are most of the times beyond their professional commitment towards the clean room facility. So we have Manuel, Maria, Andres, Fer, Ivan, Andres Valera. In the old days, it was Juan, Patricia, also Andres Black. Also the team from the Centre of Astrobiology. Maite is actually a technician, paid by the Centre of Astrobiology, but she spends the whole day working there. And also there is one thing about these people, is that many of them hold PhD. So Maria is a PhD in chemistry, Fernando and Manuel PhD in physics, Maite is an chemical engineer. So they have a scientist background. And this is super important because many of the times scientists want to use the facility, but they don't know how to nanofabricate. So you really need to have personnel like this that is super qualified. Many times you need PhDs to run these facilities because they are the transducers between the scientist community and the tools, right? So it's not only that you can have technicians, we do have technicians as well, but it's important that you also have high qualified people working there. And also I have my group, and many of the group also helps running the facility, or they suffer me being overlooking at the facility instead of looking at the science that they produce. So now our vision is the beauty emerges from the mixed states. So we want to mix people with different backgrounds. We want to have tools that can do. They are not the best at doing one job, right? But they can be combined with other tools to do things that no one else can do in a traditional clean room. Okay. Usually our building blocks, so we know how to work with quantum dots or nanocrystals, 2D materials, carbon nanotubes, graphene a lot. Most of the times, I would say 90% of the times, the substrate is silicon, but we also work with other like sapphire or glass or, well, you name it. But I would say 90% of the times we use silicon substrates. We work a lot with superconductors because this is what the space community is requiring. Also work a lot with quantum technologies community and then mostly metals. Okay, I'm pretty sure that most of you are fully aware of the micro or nanofabrication workflow. Is someone else that is not familiar with how this works? Well, just a reminder. So nanofabrication is mostly based in lithography, and lithography is the equivalent of the Gutenberg press. So Gutenberg invented this in 15th century for being able to replicate words real fast. Now, over 300 years later, 350 years later, Alois and Frende invented lithography, which is the equivalent of the Gutenberg press, but for paintings. Okay, and this is what nanofabrication is all about. So replicate drawings. Okay, and usually the workflow is you start with a master design, you pass it into a replica in the intermediate mask, then you fix it, doing something else with it. It's mostly either etching or depositing something on top or implanting an ion. Then you inspect, you repeat this, and usually you have to do many of these cycles before you end up with a device. And this is the same thing, but in different schemes. So most of the times you start with the substrate, and you have your pattern design, and you need to fix it into the substrate. So you're going to use an intermediate mask, which is a resist. And this resist is sensitive either to photons or to electrons, right? And what you're doing is you expose the resist. You can expose it with photons or with electrons or with ions, and you change the properties of the polymer. So you change your solubility of the polymer. So when you put the resist in a solvent, those regions that have been exposed either stay or either go. So you open windows in the resist, and then once you have the windows, you have your pattern there. You can either deposit things on top of the resist, and most of the material is going inside the windows, also on top of the resist. Then you remove the resist, and this is how you create a design. So this will be like a bottom-up approach. Or you can use the windows to etch down, and you end up with a relief like the Surni Manipal reliefs of the 16th century. So most of the times you need a wet lab. We have 5 of them. Solvents, acids, HF, and then we also have 2 more just for resist, either deposition or development. And they are class 10 inside because they take the air from the clean room. And they are fully equipped with everything you need to do those processing in a safety environment. In particular, the HF, which is super dangerous for humans. And we were following an approach that is called an angel. So the operator is doing his stuff on the HF hood, and then there is an angel outside the room waiting to check that nothing happens. Lithography is the most important part. So we are going to expose the resist, and we are going to transfer into the resist our master design. We can do it with photons, we have a maskless lithography tool that is capable of taking up to 20-inch wafers, but our clean room is designed for 4-inch wafers. Okay, so we can run a 4-inch wafer in all the tools that we have, but some of the tools are capable of doing larger sizes. The way it works is just a laser that exposes the resist, so your master design is a CAD file, and what you do is just pass the CAD file from your computer into the resist by exposing it with a laser. Here are some examples. So you see this is a shadow mask that we have produced with this. This is 4-inch wafer with pixels. There are kinetic inductance detectors. It's made of superconductors. This is also superconductor. The good thing about this tool is that you can run very high aspect ratio features. For example, this is a 2 millimeter bridge, but it's a 1 micron gap in between the two electrodes. This is super difficult to do, okay? And this is something, sometimes this is what really matters, is not how small you can go, but what's the aspect ratio that you can achieve with your tools. Right? In here is an aspect ratio of 1 to 1 million, which is amazing, to be honest. With this we can produce a falling wafer, but we also can produce a shadow mask. And the good thing is that in your CAD design, you can include many different chips, and then you just dice them, and you can have many different designs printed together. You pay the price, and the price is that this is a very slow process. So a full 4-inch wafer takes around 10 hours to be exposed. Okay? The good thing with this tool is that you can also do something called correlative lithography. So for example, you can have a 2-dimensional material flake. You have a pattern design, so your substrate has some initial aligning marks, okay, that you have designed with the same tool, and then you just put your flakes onto the surface, you take a picture, and we are very good at taking this picture and defining the coordinate, the absolute coordinates of this point, so that the tool can look at those coordinates and can realign itself, so that we can actually put contacts with very high precision and accuracy into the flake. This is the final device. The good thing is that we can do this with very high precision, and because, like I said, most of the times you need to do these steps many times. One important thing is that you have a very high resolution when you reposition yourself with respect to the previous lithography process that you have finished. And this machine has an interferometric state, so it's very good at doing overlays. Okay, you can have resolutions below 100 nanometers. So you can reposition yourself one layer with respect to the other with 100 nanometer accuracy. The drawback of this machine is that because it uses a laser and it uses a very high numerical aperture objective, the depth of focus is super small. So your resist layer has to be also very thin. So usually you can expose thickness of between 100 nanometers up to, let's say, 2 microns. But you cannot go any thicker. So if you want to use your resist to produce very high aspect ratio etching profiles, you cannot do it. So what you need is a mask aligner, where you can expose using a shadow mask. This is the conventional way of exposing things. You take a shadow mask, you put it on top of your resist, and then you illuminate with UV light, and in parallel you expose thousands of devices in one go, in 10 seconds. So you can expose the full 4-inch wafer in one single shot. And the good thing is that you can go really deep. So I mean, this is a 250 thick resist, right? And you can expose all the way down. So this is the way you can produce very high aspect ratio features on very thick resist. Okay? Now we have other ways. So when you use photons, you are limited by the diffraction limit of light. So you cannot go below your wavelength. So this laser is 4 or 5 nanometers, and this means that the minimum feature size you can achieve with this tool is half a micron. If you will need to go smaller, then we use photons. So we do the same thing, but we use a resist that is sensitive to electrons instead of sensitive to photons, but you do exactly the same thing. And this is an SEM with a pattern generator very powerful one from Rife. It's 400 megahertz and 14 bit per channel. So you can have, you can expose, let's say, like 500 micron by 500 micron right fields with a resolution of 2 nanometer precision in the positioning of the beam. So we can do pretty amazing things, like, for example, these CBEC nano antennas. They are made of 2 different materials. It's 2 different E-beam exposures. So one E-beam exposure for this one. These are around 50 nanometers thick, 200 nanometer wide. You see it here. So you start, and these are made of titanium nickel. So you start with nickel, and then you need to reposition yourself and make sure that the CBEC antenna, it has to be perfectly aligned with the other, because you need to create a dipole between the 2 of them. And you can see here that we can obtain, I would say this is within 10 nanometer accuracy, the offset between one dipole and the other. So we are pretty good at doing this kind of stuff, okay? Because we are interested in doing things that no other clean room can achieve, okay? But you can do other things, like this is a grating made on silicon. You can do, for example, very narrow gaps between electrodes, and then you can use dielectrophoresis to put a single carbon nanotube in between the 2 of them. Or you can do very thin and very long meander structures. This is a superconducting nanowire single photon detector, for example. Sometimes you don't need the resist at all, so we skip these steps, and now we are going to use the electron beam and the focus ion beam either to do bottom-up structures or top-down structures. So for that we have a focus ion beam, and for those Star Wars fans, this is exactly an ion gun. So what you do is, this is an NSEM, this is a focus ion beam. This means that you can look at with electrons at the same time that you are milling with gallium ions. And you can see the process being recorded here. This is real time. This 100 nanometer thick gold layer on top of a silicon substrate. And we are producing some ring resonators, plasmonic ring resonators that are 1 micron in diameter. And the rim is about 100 nanometers. Right? So you are directly milling the structure. You don't need to go through all the other steps. The good thing with the ions is that you can also use the ions or the electrons either to deposit things or to etch materials. So we have a gas injection system with 5 needles, and we can use them either to deposit tungsten carbide, gold, or silicon dioxide. There's 3 of them. And then we can use the other 2 to do assisted etching. So it's either iodine or xenon fluoride. And you can see here some structures being deposited. So we start with some electrodes that we have produced either with the Heidelberg or with the mask aligner. This is gold patterns. And then, so we have these ones. And then we have deposit with this needle here, a tungsten carbide nanowire. And again, this nanowire is 100 microns long, 100 nanometers wide, 100 nanometers tall. And it's superconducting. The tungsten carbide has a critical temperature around 5 Kelvin. So for example, you can do split ring geometries. This is something that it will take you a really long time to do with the standard of nanofabrication approach. You can also deposit things. So for example, this is, we create the nanowire, but now we want to apply an electric field. So we deposit a pad of silicon dioxide, and then we deposit another wire on top. And this nanowire now is going to apply a bias between this electrode and a bottom gate. We can do also etching, assisted etching. So this is real-time milling of a silicon dioxide layer on top of silicon. And because the etching ratio between silicon dioxide and silicon under xenon fluoride gas is very different, silicon gets etched much faster than the silicon dioxide. So in this way, we have created this nano-harp structure. So now these are beams hanging because they've been released from the silicon substrate, just on one go. We can also use the silicon, the xenon fluoride to etch 2-dimensional materials after they've been produced. So we produce the device, this structure, but now we can modify the geometry. Like if you have a nano scissors and you can cut the regions of the 2-dimensional flake that you don't want, or you can do this meandering structures, quantum column blockade structures, or whatever. There's also a third way of doing nano-imprint, which is nano-imprint. So the way it works is you create a stamp and you use like a Gutenberg press to reproduce the features in your master stamp into a thermoplastic. We have two different tools. One is small, it applies temperature and pressure, and one big that applies temperature, pressure, and UV light. And in this way, you can modify the physical, the chemical, and the biological properties of this thermoplastic. So for example, you can replicate the moth eye. The moth eye is a bactericidal, so this is a real moth eye. This is an artificial moth eye that we have created in a polymer. And you see this becomes bactericidal. This is Staphylococcus aureus, and you see that the bacteria are being killed when you put them on top of the surface. We also have a roll-to-roll version outside the clean room of these tools. Well, thin film growth. Once you have your resist with the windows, you need to deposit something on top. Most of the times it's a metal or an oxide. So we have two different tools. One E-beam, very large, for non-magnetic metals and for superconductors. We can deposit niobium, for example. And then we have a thermal evaporator. This is E-beam. The E-beam also has a Kaufman ion gun. So we have argon, so we can do, sometimes we can expose some of the windows in the resist to an ion milling prior to the evaporation of the metals. We also have an atomic layer deposition, very, very massive tool. It's 12 lines, 6 for plasma, 6 for thermal evaporators. It's got also an ozone generator. So we can run pretty much every ALD process you can dream of. But we tend to use it only for oxides. It's hafnium oxide and silicon oxide, titanium or manganese. And you can see here an example is this is a fiber made of carbon nanotubes. And with ALD, you can go conformal. So in every nanotube, you can grow a conformal coating of whatever material you want. So you can see here, we have grown a titanium oxide. In every nanotube, we have grown a titanium oxide 20 nanometer layer, and this is a thin oxide. We also have a sputtering system. It's the uniqueness of this system is that it can achieve very high homogeneous thin films, well below 2 sigma in a 4-inch wafer. This is what you need if you want to produce wafers for a space community. So sometimes you need to go the other way. You need to etch materials instead of deposit materials. And for that, we use cryo inductively coupled plasma reactive ion etcher. You can have different chemistries. We don't have chlorine chemistry, because chlorine is available at the time, and chlorine was available at the Instituto de Micro y Nanotecnología. So I opted to go the fluorine approach. So we have CF4, SF6, CHF3, whatever all possibility of fluorine chemistries that you may need. And this is useful because you can etch away, for example, nanofluidic stamps to do. This is a master stamp, and with this master stamp, you can produce micro-fluidic channels, or you can go very deep because this is cryo, so the sample sits at 77 Kelvin. And the good thing is also that with the cryo version, you can control the tapering angle of the walls that you are producing. You can go either positive angle or negative angle. And this is very unique because it can Oxford warranties you that you can go 1:10 aspect ratio. So for example, these are 200 nanometer wide pillars, and they are 2 micron deep. This is probably the highest you can go with this type of approach. We also, this is the father, this is the son, so the smaller version. It's also reactive ion etching that we use for 2-dimensional materials. But it's also pretty good to etch some metals like niobium. So for example, this meander here has been etched using this tiny reactive ion etcher. Sometimes you need to do surface treatments, so to make things that, to make sure that the final device is clean and is pretty. So we have rapid thermal annealer, plasma cleaner, ozone cleaner. The rapid thermal annealer is pretty unique because it can achieve, I mean, you can bake the cake real fast. So you can achieve 1,000 Celsius degrees in just 10 seconds. right? So this is what you need many times to amorphize materials or to create an ash out of the resist that you can remove later really easy. And of course, another important thing is that we work with a wafer, but many times you don't want to put the wafer in your final experiment, but you need to dice it, right? So we have dicing tools. So this is a way we can take the dice out of the wafer. And most of the times we work with optoelectronic devices, and you need to connect them to the outside wall. So for that we have a ball and wedge bonder system. So this is precisely when you have your die in your sample holder, you can put micro wires, either gold or aluminum, going from your path in the chip to the chip carrier. Metrology. So you need to check from time to time that everything you're doing is accurate to the master design that you started with. And for that, we have the most important tool to me. This is detector profilometer. It measures steps, either down or either up. It's just a stylus that goes into the surface. It works like an IFM, roughly. So when it finds an object, it goes up and it tells you what's the thickness or what's the depth of that feature. But this detector is being calibrated using a standard sample. This standard sample comes from the National Institute of Standards and Technology, from NIST. We send it over to recalibrate every 6 months. And every month we calibrate this machine with that standard. And this machine becomes the reference of all the tools that we have in the clean room. So when we say that we have deposited 100 nanometers of gold with our evaporator, we say it because the evaporator is calibrated with respect to this machine, and this machine is calibrated with respect to a standard certificate master design. Of course, we have several optical microscopes and stereo zooms. We have a probe station with a parameter analyzer, so we can check the electronic properties of the devices, final devices, or while we are producing them. And we have two SEMs, identical columns, a Gemini column from size, two different versions. This is a Sigma version. This is an Omega version. This one is variable pressure, and this is useful when you want to look at things that are not conductive, right? So, for example, textiles, polymers, things like that. And also, it's equipped with a rather powerful EDX system, so you can do material science and you can tell what's on your surface, what's on your device. And this one is inside a clean room, and it's equipped with a scanning transmission electron detector, so you can do STEM measurements, and you can increase the resolution, I will say, by a factor of 10. So when you are in SEM mode, the minimum feature size that you can look into is around 5 to 10 nanometers. But if you go into STM mode, you can go to, let's say, half a nanometer in resolution, like in this case, these are carbon nanochips. It also has a charge compensator, so we can also look at non-conductive devices using the charge compensator. So, how to access? So I was asking, many of the tools that you've seen, they are self-service. So you come, you get trained, and you use them by yourself. Other tools that are super expensive, like the lithography tools, what we do is we have this pilot approach. So we have a technician that drives the machine, but you can come and sit next to him or to her and tell, okay, I want this lithography to be made in this region of the sample or in this other region of the sample, and it's just, you are the co-pilot, and the technician is just the pilot running the machine. You can, most useful way of getting access is just writing an email to nanofabrication@IMDEA.org, or if you forget about this, if you Google IMDEA NanoFabLab, you will get to this web page, and in this web page you go to localización y contacto, and there's a form there. You just fill in the form, click send, and we will receive your request. Usually after some days, we will contact you back. We'll make sure that we understand what you want to do, and then we will prepare a quotation. Everyone pays here, okay? The tariffs are super small, but everyone has to contribute because this is the only way that we can keep the clean room up and running. Even in the people place, and there is a tariff, there is a unique tariff for all the users coming from the campus of Campus de Excelencia. So anyone in the Campus de Excelencia, like you guys, like Cerámica y Vidrio, like the people in the Facultad de Ciencias, like the Instituto de Micro y Nanotecnología, and the IMDEA people, we all pay the same price, okay? And sometimes I've been asked, okay, can I do a collaboration with you guys so I don't have to pay? Well, the answer most of the times is no, right? So when is a service, when is a collaboration? When we know how to do it, okay, everything that it's been a standard that we have developed, that we really know what you want and we know how to do, then it's a service, we pay. Again, it's very low price, so if the e-beam, if 1 hour of e-beam costs us 100 euros per hour, we are going to charge you probably 20 euros per hour. Okay, so it's very low tariff, but it's going to be a service. I mean, we do what you need, you take your device, you off you go to their lab, and you use it as you want, you publish whatever you get out of it, and we don't participate in that part because it's a service that you have paid for. Sometimes you have a request, say, I want to do this, and you don't know how to do it, and we don't know how to do it. Then it's a collaboration, because then we need to involve and we need to think like scientists and not like technicians running the clean room. We need to think like, okay, how do we do this lithography on top of this material, on top of this substrate, which is not a standard procedure for anyone else. Okay, and this is a collaboration. And in a collaboration, we still pay, but we usually get an agreement of okay, like, let's say, maybe sometimes you don't pay anything, sometimes you just contribute with your samples, sometimes you contribute with the substrates because they are super special, and then we share the science together. But usually we agree on this at the very, very, very beginning. So we are going to let you know, okay, this we have to do it as a service, or I'm sorry, this is something that you're requesting something that we don't know how to do. Okay, and if you want, we can help you out to develop it together. Does it mean it's going to be a collaboration forever? No, because at some point it will become something that we know how to do, and then it will be a service, and then you will be access to that service as anyone else. Acknowledgements. I have to acknowledge, of course, all the funding governing boards, of course, the institutions that have contributed, the Campus de Excelencia CSIC, my institute IMDEA Nano and the Centre of Nanofabrication. I have to acknowledge all the institutions that have contributed one way or the other. Money is important, but what is vital is the people. So I have to thank so many people that have just opted to put just an icon, because most of the times I forget someone, and then someone gets pissed. You won't believe how many people has contributed to make this a reality. It's hundreds of people, so I have to be super thankful to all the people that has contributed. And before we finish, because I always like to dream and to aim for the stars, I mean, it was time, I think it was back in 2013 that I was giving a lecture at the Instituto de Micro y Nanotecnología, explaining something similar about the clean room was not so mature as it is now, but I was explaining the project that we were having. And at that time, I said that nanofabricating is expensive, and it's becoming more and more critical for countries and for regions, particularly now that you've seen there's a chip war all over the world, and there's this chip act initiatives in Europe, there's chip act initiatives in the States, in Japan, in China, in Taiwan, in Malaysia, well, you name it. So it's becoming more and more important that we join forces if we want to keep up and running, producing science with this type of devices that require very expensive facilities. So at some point, I proposed back in 2013 to create a network of clean rooms in the Comunidad de Madrid, and it's taken me only 14 years of my life, but this is close to a reality now, right? Because I'm now the director of this cluster, and I have access to the decision makers, and I think I have 99% convinced them that they need to put money to create this network. So what I want to have is all the information of all the clean room available in Madrid. No matter if you are super clean, super gray, super big, super small, it doesn't matter. We really need to know what we are capable of doing in our region. And we need to make sure that we stay together to be competitive with other regions in Spain, but also with other regions in Europe and to other regions in the world. Otherwise, we will become less and less competitive scientifically wise, right? So this is my dream. And this is the end of the talk. So thank you so much for your attention. It's been 45 minutes. Thank you.
For this interesting talk about all the possibilities that we have very close from here. So is your time for questions?
Yeah, sure.
I wonder if, for example, one is want to, I don't know, to work in such clean rooms or something like that. Which are the academic qualifications or the professional skills to work in? And if there is any opportunity or chance to, I don't know, if you are advanced in your scientific career to become a technician or one of the pioneers of inside that.
Europe is going to require over 500,000 technicians in the next 6 years, from now till 2030. So it doesn't matter your qualification. I mean, if you're skilled and you're willing to learn, then you will have an opportunity to work either in my facility or in many of the facilities that are being developed all over Europe. So I mean, it doesn't really matter. You can be. I mean, I have in my team, I have chemists, physicists, material science engineers, graduados de FP. I don't know how to say it in English, but well, professional technicians. I once had a guy coming from the army. I once had a psychologist. I mean, it doesn't really matter. I mean, there's so many work. The workload in the clean room is so high. There's so many tasks that we need to address that some way or the other you will find a way of being impactful in the team. So it doesn't really matter. But of course, if you understand. If you have a scientific background or an engineering background, you understand in depth the tools, right? Then I think you can really push them to the limits sometimes when you understand the physics or the chemistry behind the tools you're using.
A very technical question about focused ion beam. No, I mean, I want to do optical antennas, very sharp tips.
Mm-hmm.
Do you have some experience on doing those?
We've tried sometimes.
Mm-hmm.
Focused ion beam has got its goods and its bads. The goods is that you can achieve very narrow resolutions, and in one go you can have your antenna up and running. But our FIB, our FIB, is based on gallium, and it produces an awful lot of amorphization.
What?
Amorphization.
Ah, okay.
So if you start, let's say, with a polycrystalline tip, and crystallinity of the tip is important for your antenna, then it will become super amorphous, right? And then an amorphous material.
What about the radius of curvature? Which is the sharpness?
Oh, the sharpness, I mean, it can get down to 10 nanometers.
Oh, maybe
doesn't really matter.
maybe
The other problem is that gallium gets implanted, right? So, I mean, we usually work with a 30 kV acceleration. Our FIB is very powerful because it's one of the only columns in the market that allows you to go between 5 kilovolts or 1 kilovolt all the way up to 30 kilovolts. So you can control the profile of implantation of the gallium. But the gallium is going to stay there forever. So these days, focused ion beams are moving either to hydrogen or to silicon or to argon or to helium to make sure that the implanted ions that do not crosstalk with the final device. So if you have an antenna, you want to have it made of gold, right, because you use a plasmonic antenna or whatever, then the gold will be contaminated by gallium as well.
But what is the depth of this implantation? Hundreds of nanometers?
It depends on the kilovolts that you're using. So it's between, it depends also on the substrate, right, and the crystallinity of the substrate.
No, because this will be a wire for me. Okay, we can talk later.
Yeah, but It's usually between few microns and 100 nanometers, something like that.
I have a question myself.
Yeah,
What
sure.
about the companies? You said that there are some companies in the
Oh, yeah.
community of Madrid that are approaching you.
Yeah, yeah.
There are many, or can you tell?
There's
us?
I would say it floats, but I would say it's around 10 these days. It's becoming more and more required, so I think the number of companies that come to visit us and to request to us to do something is also increasing, which is good. So I think companies are becoming more and more technological, and technology is becoming more and more, how to say it, many companies that were producing somewhere else in the world have decided to produce inland. And this is one of the reasons why, after the COVID, and after many of the disruptions that happened to the technology value chain have been modified, and many companies that were producing in the East countries are now producing in Spain.
More comments?
Hi, I have a technical question. The sputtering, you can perform multi-layers with good accuracy, or I mean, how automatized is it?
No, it's
not.
It's not automatized. So you have DC and RF. We have 5 different magnetrons.
Mm-hmm.
2 are RF, 3 DC ones, but you have to do it manually. We can do niobium. It's a reactive sputtering, so we can do titanium nitride, niobium nitride, niobium titanium nitride, aluminum nitride, aluminum titanium, and so forth and so on. But it's not automatized. We can produce by layers, but the thing is that this is only for space projects, and therefore no resists are allowed to go into. So if you want to do anything with metals deposited in the sputtering, then you always have to go the top-down approach. So you start with the substrate, then you produce the thin film, and then you etch around. Like, for example, imagine you want to produce this meander. This is niobium titanium nitride. So you start with a thin film of niobium titanium nitride, and then you etch around all the niobium titanium nitride that you don't want, and you stay. Because resists are not allowed, so you cannot do a lift-off process in the sputtering.
And I have another question.
Sure.
But this one related with the access policy. You distinguish between services with self-service access, and you mentioned that it's not for lithography, including the optical with the laser, or?
Yes.
Okay.
Yes, those lithography tools are only handled, I would say 99% of the times, by our internal technicians. Sometimes there's a group, Eduardo Lee from the Autónoma, for many years. He has been accessing the tool himself with his team. Why? Because he was a very knowledgeable user. I mean, he was using a similar tool in France for over 10 years, right? So I mean, it doesn't make sense. He probably knows more than my technicians do. Well, I doubt it, but probably he thinks that he knows more. So he was allowed to use the machine. So if you come and you show that you are responsible, that you have proficiency, that you are knowledgeable, then there is an option that you are allowed to become a super user, and therefore you have access to tools that usually are not open to external users. But you have to keep in mind that we only do it if you guarantee that you are becoming a super user for a long time, right? Because the training curve of these tools is very hard. So it takes many years to really learn all the properties and how to really milk the tools, right? So it's, to me, if you're going to come with a student or with a postdoc, and he's going to stay there for 2 years, to be honest, it's not worth it to get trained, right? I'm being honest, it's not worth it to get trained. You need to spend hundreds of hours sitting on the tool, and then if you're going to leave in a couple of years, then it's a waste of time, and it's a waste of money for everyone. Yeah, Eva?
I'd like to ask about the quality certification of the clean room. I don't know if you have it or if you are planning to
We don't have it.
one. Or
No.
if you think if it's worthy, are you planning, or your opinion also
Yes,
about this?
of course it's worthy. Many of the companies request you to be qualified, but we have a security clearance, a NATO security clearance. And this means if I want to get certified, then I need to put in a piece of paper that is public what I have, what's the size of my clean room, what my procedures are, and this is incompatible with having a security clearance. So you have to either go one way or you have to go the other. And I opted because there are other clean rooms, like the clean room in the micro nanotechnology that is ISO 9001 qualification. So I mean, if you really need to have that in your process and you're a company that requires to have that, then look, I mean, if we work together, this is the whole thing. If we work together and you come to me and you need that, I'm going to say, look, go to Toscantos next door and they will do it for you, right? But if you're a security company or you're a defense company, then you need to do your stuff in an environment that has this kind of certification. So,
Okay.
like I said, I don't want to compete. I just want to create value for the whole Comunidad de Madrid. So, I mean, some of us will require to go the security clearance way, and some of us will go the ISO way, and between all of us, then we can provide value to all the companies and to all the scientists in the Comunidad de Madrid.
Okay, thank you.
Sure.
Some more questions, comments? No? So thank you again.
My pleasure.